Swayam Prabha. Digital India. Educated India.
So, there are two scientists long back, more than 100 years back. They have devised a very interesting experiment. Okay, it's called as Michelson-Morley experiment. What they showed, I will not describe the details of the experiment, but what they showed is something which is quite remarkable, and then it changed the way, it changed the physical laws completely, the form of physics. What they showed is that the velocity of light is independent of the source, the velocity of source or whatever. It is independent of which inertial frame that you are in. This is very counterintuitive, because suppose you are traveling on train. Okay, let's say the train makes a uniform motion. Okay, and then in the train you are on the ground, and then your friend is on the train. So this is a train which moves along this direction. You are sitting in ground, and then in train you just throw a ball here. Okay, so suppose the train moves with a velocity u along this direction. You throw a ball with velocity, let's say v. Then if you are on the ground, then the velocities will just add. Okay, for you, if you consider v prime to be the velocity of the ball, okay, then you will see v prime is just u plus v, because u is the speed in which the train moves, and v is the speed of the ball inside the train. Therefore, the speed of ball for you will just be the sum of these two. Okay, so therefore that's the same way you might naively conclude that if you emit a light signal here, suppose the speed of light is c, then the speed of light as observed by you should actually be u plus c. That is what is the naive expectation. But Michelson and Morley has experimentally proved it to be otherwise, and there are many more experiments which has been done later on, and it has the same conclusion. So the conclusion is that if you go from one inertial frame to another inertial frame, then the speed of light does not change. And so therefore, we are talking about all these transformations. So therefore, we can just now ask, so far we have talked about orthogonal transformations. Now what about the transformations which keep the velocity of light invariant? The orthogonal transformations are the transformations we have obtained by requiring the length of a vector to be unchanged, right? So far we just said what happens when you require the length of a vector to be the same, and then this is all that we have obtained. Now we can ask what happens to the set of transformations which keep the speed of light to be the same. Now what about all these transformations that we have discussed? If you make a rotation, of course the speed of light does not change. Okay, so they are also a kind of valid transformations, but they are a subset of all transformations which keep the velocity of light invariant. So we will ask, what are all transformations which keep the velocity of light invariant? Like here we have asked, what are all transformations which keep the length of a vector remain unchanged? And that's how we have obtained all these three parameters, R transpose R equal to identity, all these things that we have derived. Now we will do this thing. So if the speed of light remains unchanged, c square t square minus x square minus y square minus z square. This is the quantity which remains unchanged. If c is the speed of light, okay, then you look for a class of transformations. You look for all set of transformations for which this quantity just becomes 0. Okay. So whether you consider this or you consider c square t prime square minus x prime square y prime square minus z prime square equal to 0. Okay. What are all the linear transformations which keep this quantity invariant? That is what we ask. Now, if t prime is equal to t and x equal to r times x prime equal to rx, where x is just this r transpose r, then of course that keeps this invariant. Okay, this is just our standard rotation. Standard rotations keep this equation invariant. They keep the velocity of light invariant. Apart from that, there are also other transformations which keep this quantity invariant. And then we will ask what are these transformations and then how physically we can interpret these transformations. Okay. So we will just the previous way, just like that, we will again write them in terms of matrices. Okay, it is very easy if we express our equations in terms of matrices, then we can understand them in a more straightforward way. So what I will do, I will introduce the notation x0 to be c times t. Okay, this is a new notation, but x1 is just x, x2 is y, x3 is z. Okay, so then what happens? This equation is nothing but c square t square minus x square minus y square minus z square, and I will call, what will I call? I will call maybe this capital X. I have called in the earlier thing, I did not. What should I? Let's call it chi. Okay. So chi is just this: x0, x1, x2, x3. Okay. This column vector. So this quantity will be chi transpose. Let me write it this way. Okay, it is just x0, x1, x2, x3 times, I will write this in a fancy way. Okay, 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1 times x0, x1, x2, x3. Okay, so I will call this to be chi. I will call this to be eta. So this quantity is chi transpose eta chi. Now I cannot write something like r transpose r or x transpose x. I write it this way. Okay. And I ask, what are all linear transformations which keep this quantity the same, this quantity invariant? Okay, so linear transformations are again this. Suppose chi goes to chi prime. If it is a linear transformation, then I can write it like, so chi is a column vector. I can write it as lambda times chi, where lambda is a 4 by 4 matrix, right? A linear transformation can always be represented this way. Is this clear? In other words, what I am saying is, x0 prime is some lambda 1 1 x0 or lambda 0 0 x0 plus lambda 0 1 x1 plus lambda 0 2 x2 plus lambda 0 3 x3. This is a linear transformation, right? x1 prime is lambda 1 0 x0 plus lambda 1 1 x1 plus lambda 1 2 x2. Similarly, x2 prime is lambda 2 0 x0 and so on and so on. x3 prime is lambda 3 0 x0. This is the most general linear transformation. If these lambdas are constants, then this is the most general linear transformation which relates x0, x1, x2, x3 to x0 prime, x1 prime, x2 prime, x3 prime. So this relation, I can write it in terms of matrices like this. This is our chi prime. This 4 by 4 matrix, lambda 0 0, lambda 0 1, lambda 1 0, this I will call as lambda. So this is the most general linear transformation. Now what I require? I require this linear transformation to keep this quantity invariant. That is my basic requirement. What are all linear transformations which keep this quantity unchanged? So let us see what does it give. So chi prime transpose eta chi prime. This quantity should be same as chi transpose eta chi. And what is chi prime? It is lambda chi transpose eta lambda chi, and this is nothing but chi transpose lambda transpose eta lambda chi, and this quantity should be same as this. If you do not want to impose any restriction on x0, x1, x2, x3, then the only way this will be equal to this is if lambda transpose eta lambda is same as eta. So you consider 4 by 4 matrices which satisfy this relation. Okay? So that will give us linear transformations which keep this quantity invariant. Okay? So they are the transformations which keep the velocity of light invariant. Now, what are these transformations and how many such transformations are there? How many independent parameters are there? Again, we can discuss about discrete transformations. Let us not worry too much about the discrete transformations right away. Let us look at the continuous transformations which are described by a set of parameters. And then let us ask how many parameters are there which describe such transformations. So how many parameters will be there? Who can tell? In general, 16. If there is 16 is the most general linear transformation. But you see, the transformation has to satisfy this relation. Very good. So this is 4 because it is symmetric. You see. So symmetric basically means it gives you 10 equations. Okay, it is a symmetric 4 by 4 matrix. So 6, not 4. Okay, so lambda has 16 4 by 4. So there are 16 parameters. This is a symmetric matrix. Okay, so it gives you 10 equations. So there are 16 parameters, but there are 10 constraints. Therefore, there are 6 free parameters which are there. So this is a 6 parameter family of transformations. So we have a 6 parameter family of transformations which keep the velocity of light invariant. Now we have already seen if you make a rotation, the velocity of light remains unchanged. So the rotations take away 3 parameters. Okay, so I already know if I make a 3 parameter family of transformations which are rotations, that will keep the velocity of light unchanged. So there are 3 additional parameters other than rotations which keep the velocity of light unchanged, and these are basically called as boosts or Lorentz transformations. Actually, this itself is called as Lorentz transformation in a more abstract way. Any transformation which keeps the velocity of light unchanged is a Lorentz transformation. So a Lorentz transformation consists of rotations and Lorentz boosts. These are basically Lorentz boosts or Lorentz transformations. So let us try to see a particular transformation, a particular one parameter family of transformation which is not a rotation and which keeps this quantity unchanged. Okay? Like in the case of rotations, we considered a simple example. We considered a rotation about z-axis. So what did a rotation about z-axis did? It mixed only x and y coordinates among themselves. So exactly the same way, we will consider a transformation which leaves these two unchanged, which mixes these two. Okay? If it mixes these two, it's a rotation. If it mixes these two, it's again a rotation. If it mixes these two, it's again a rotation. Okay? So we will not worry about the ones which mix x0, x1, x2, x3 among themselves. They are basically rotations. So we will consider a transformation which involves x0 and any one of them. Okay? So there will be 3 such independent transformations. One is if you have a transformation which mix x0 and x1. You have a transformation which mixes x0 and x2. You have a transformation which makes x0 and x3. Any other transformation will actually be a combination of these transformations. So we don't have to worry about them. They are not independent. These are all independent transformations. So the 3 parameters are basically explained here. Okay? So the 3 parameters involve one which mixes x0, x1, another which mixes x0, x2, and the third one which mixes x0, x3. Okay? The first one is called as a boost along x1 direction. The second transformation is a boost along x2 direction, and the third transformation is a boost along x3 transformation. And you will see little later why I call this to be a boost along these directions. But let us just keep the name as such, and then let us see what can we say about the transformations. Okay? What is the general form of these transformations? Okay. So I will not worry about this. I will worry about the transformations which only mixes x0 and x1. Okay. So therefore, what is the condition that I have to worry about? It's just this x0, x1, 1, 0, 0, minus 1, x0, x1. This quantity should actually be x0, x1, right? I should just worry about this. Or equivalently, if I express it in terms of lambdas, then I don't have to worry about the all other components. I only have to, so it's a 4 by 4 matrix, but I have to worry about only lambda 0, 0, lambda 0, 1, 1, 0, lambda 1, 1. I only have to worry about this. Okay? All these things I can set this to be 0, this to be 1, 0, 0, 1. So what are these lambdas which keep this unchanged? Okay. Now, if it was a rotation, okay, suppose it was a rotation, then you immediately you can see what is, how are x0 prime, x1 prime related with x0, x1, right? Suppose I had this plus 1 instead of minus 1, okay? Then it would just have been a rotation. And we have already discussed for a rotation, this is nothing but cos alpha minus sin alpha, cos alpha, x0, x1, right? This is how it is. But unfortunately for us, it is not a plus 1, there is a minus sign here, okay? So we have to worry about this. Now, without deriving it, I will just tell you the answer. What is the most general solution to this? Again, it will describe a one parameter family of transformations, and these are basically the hyperbolic functions. So this is just cos hyperbolic alpha, sin hyperbolic alpha, sin hyperbolic alpha, cos hyperbolic alpha. Hyperbolic functions, many of you may not be aware of these, okay? So these are basically exponentials, all of you know, right? Okay? So cos hyperbolic alpha is just half exponential alpha plus exponential minus alpha. And sin hyperbolic alpha is half exponential alpha minus exponential minus alpha. Okay. They have very interesting properties. One interesting one, which will be useful for us, one interesting relation that is useful for us is the following. Cos hyperbolic square alpha minus sin hyperbolic square alpha is equal to 1. Okay. you can see it clearly. If you take cos hyperbolic square alpha, it is just 1/4 e to the power 2 alpha plus e to the power minus 2 alpha plus 2 minus 1/4 e to the power 2 alpha minus 2, and then it makes 1. Okay, so it's straightforward. And because of this property, you can see if you plug it here. So what does this relation give you? This relation gives you this one is cos hyperbolic alpha sin hyperbolic alpha minus sin hyperbolic alpha cos hyperbolic alpha 1 0 0 minus 1 right, and this is nothing but it is just if you multiply this, you see you will get a cos hyperbolic square alpha minus sin hyperbolic square alpha 0 0 sin hyperbolic square alpha minus cos hyperbolic square alpha. Okay, so this is nothing but 1 0 0 minus 1. So the moral is that if you make a transformation like this, it indeed preserves this. Okay, so it looks very much like rotation, except that instead of cos and sin functions, they are replaced by cos hyperbolic and sin hyperbolic functions. Okay, and sometimes that's why they are called as imaginary rotations, because you see cos hyperbolic alpha is just half e to the power alpha plus e to the power minus alpha. Instead of alpha, if you put I alpha e to the power minus I alpha, you get this cos thing. Okay, cos theta is half e to the power I theta plus e to the power minus I theta. Similarly, sin theta is just 1 over 2I that thing. And okay, so this is a particular example of a transformation which mixes x0 and x1 non-trivially, and it preserves that relation. It keeps this quantity invariant. Okay. Now to understand this so we will not discuss the most general transformation. We will focus only on this transformation, and I will explain why I call this to be a boost. Okay, so instead of alpha, so x0 prime x1 prime is cos hyperbolic alpha minus sin hyperbolic alpha x0 x1. Okay, tan hyperbolic alpha is nothing but sin hyperbolic alpha over cos hyperbolic alpha. I will introduce a quantity which I will call as beta. Okay, and I will say that tan hyperbolic alpha is beta. Okay, if this is beta, then cos hyperbolic alpha is just 1 over 1 minus beta square. Sin hyperbolic alpha is beta over 1 minus beta square. Okay. You can see that they indeed satisfy this property, cos hyperbolic square alpha minus sin hyperbolic square alpha is equal to 1, and all other property. Okay. So this divided by this is beta, and so on and so forth. Okay. So I am instead of alpha is just a parameter. Okay. And instead of alpha, I am introducing a parameter beta. Okay. What is the range of alpha? It is from minus infinity to plus infinity. Okay. And this parameter beta will range from 0 to 1. Okay. Because alpha is real, it is just 0 to 1, and for positive alpha, this is what is my parameter. For negative alpha, I just take a minus sign here. Okay. So let us not worry about alpha negative. Let us say alpha runs from 0 to infinity. Okay. When alpha equal to 0, cos hyperbolic alpha is just 1. That will correspond to beta equal to 0. And as alpha goes to infinity, beta just goes to 1.
Sir, won't cos hyperbolic of minus alpha be equal to cos hyperbolic of alpha? So you don't need to put minus sign.
Yeah, so actually it's you're right.
Only for sine hyperbolic
Only
alpha.
for sine, yeah, absolutely. So actually, therefore this range of beta, yeah, thank you. So beta's range is actually minus 1 to 1. So when alpha goes from 0 to infinity, beta goes from 0 to 1. When alpha goes to 0 to minus infinity, beta will go from 0 to minus 1. And you can see for the sine hyperbolic alpha, actually this is what it is. When alpha equal to 0, beta equal to 0. When alpha equal to infinity, beta is 1. When alpha is minus infinity, beta is minus 1. So from this equation, you can more clearly see this is the range of beta, and alpha can take from minus infinity to infinity, whereas beta takes values from minus 1 to 1. Any other question? Now, if I do this, and so this is the equation, x0 prime is equal to cos hyperbolic alpha x0 minus sin hyperbolic alpha x1. Okay. So in terms of this, it is just x0 divided by actually x0 minus beta x1 divided by 1 minus beta square. Now, so beta takes values from minus 1 to 1. Let us assume beta is very small. Okay. Now we are just considering an approximation where we are not saying beta takes all values. We are just asking how does this relation look when beta is very small. Okay. If beta is very small, beta square is much, so beta is nearly 0. Okay. So beta square is very much less than beta. Okay. So to a very good approximation, we will just set this to be x0 minus beta x1. Okay. So we will ignore this beta square term here in the denominator, and this is what. And now, so this is x0 prime, this is x0, but remember x0 is c times t. Okay. So what is ct prime is nearly equal to c times t minus beta x. How is t prime related to t? T prime is related to t by t prime is let us look at this relation x1 prime. Okay, so this is how x0 prime is there, and if I look at x1 prime, sin hyperbolic alpha x0 plus cos hyperbolic alpha x1. So this is beta x0 plus x1 1 minus beta square, and this is x1 plus beta x0. Okay. So in terms of our original coordinates, x prime is nearly equal to x plus c beta times t. So this is something like you consider two observers. Okay. So suppose one is moving with a velocity v with respect to the other. Okay. And then you ask, how are the coordinates related? If you have a point here, for this observer, if this is x, for this observer, if this is x prime, how are x prime and x related if one is moving with a constant velocity v with respect to other? Then this is how it relates. X prime is just x plus vt. So this c times beta, if I identify with the velocity v, it is like a boost. Okay, you just let one of these the primed coordinate to move with a velocity v with respect to the other. That is why we call this to be a boost, and this parameter beta is identified by v by c. And you see, if the velocity is very small, okay, then you have this ordinary non-relativistic relation that you get. But if the velocity need not be very small, in that case, this is the transformation. This is how the coordinates are related among each other. So how are these transformations? So x prime is just this. So this implies t prime is t minus v x over c square divided by 1 minus v square over c square, and x prime is x minus vt divided by square root of 1 minus v square over c square. So this is how the transformation relates x and t. Y prime is same as y, z prime is same as z. These are the conventional Lorentz transformations. Okay, and these transformations relate one inertial observer to the other inertial observer, which when the observers move with a velocity v with respect to each other. If two observers move with a velocity v with respect to each other, then this is how the coordinates are related. And then in general, as we have said, this is just a particular transformation. In general, the observers can move in any direction, and then they can also rotate. So this is the general transformation, where this lambda is related by this relation lambda transpose eta lambda is equal to eta. So we have a more general transformation now, and exactly like the previous lecture, we can introduce vectors, and then we can call quantities which transform exactly the way the coordinate transform are Lorentz vectors, okay, are vectors under the Lorentz transformation. And then there are more general quantities which can transform like a tensor. We can have Lorentz tensors, and then the principle of relativity tells you that if you want to write the equation of motion, then it must be expressible as a tensor equation. Now I will give it as a homework for you to show that if you just write the standard Newton's law f m d square x over dt square or d square r over dt square is f, then this equation will not actually transform in a covariant fashion, in the sense it will not look the same if you perform such a transformation. Okay? So therefore this equation actually needed modification, and Einstein modified it appropriately so that it will respect this transformation. Okay. I will give you a classic example of a Lorentz tensor. You know electric field and magnetic field, okay? E and B. I will not explain how, but they are basically vectors. But they are vectors only under an orthogonal transformation. This is a vector, this is a pseudo vector. If you perform a Lorentz transformation, then these quantities no longer remain vector. They do not transform nicely individually. E and B do not transform nicely under Lorentz transformation. It so happens that these two combine in a strange fashion, and they form a tensor. Okay? So together they form a second rank tensor. If you make a Lorentz transformation, then the electric field and magnetic field mix each other. But they mix in a nice way such that it transfers, the combination transfers like a second rank tensor. Okay, so this is one classic example of a tensor in physics. Okay, and then you can write down the equations involving electric and magnetic field, and the principle of relativity tells you that these equations must be expressible as tensor equations. Okay, any equation you write, it must be expressible as a tensor equations, and then that actually is a great simplification, because it constrains what are the terms that you can write in your equations very severely, and then it modifies the laws of nature in a particular way. Okay. So I think with this we will close our lectures.
Thank you so much, sir. That was a very interesting lecture.
Okay.
We learned a lot of new things. I thought vectors was very elementary and was just a set of physical quantities, but then you explained a lot. That was very interesting, and we learned a lot of new things. Thank you so much,
Okay,
sir.
thank you. Oh, thanks.